4B, yeah.
Okay, 1 minute, let me open. So we are doing under what conditions? Okay, with GCD.
So basically, the point here is just to do like a parameterization.
Yes. So here actually we are finding that. So under what condition the solution exists, right? So the condition we proved that if the GCD of all of the three terms together is 1, then it has a solution, right? Right. So let us do part C. So part C is they're saying that using the from part B to find the integer solutions of to find a solution in integers 155x plus 341y 385z. So this is one. So to solution exist, we have to first verify that this thing is 1, right? Okay. So how will you do that?
So how did we approach the B, part B?
Yes. Part B we did like this, right? So we first we proved that suppose there is two directions, right? So first we assume that this has a condition, this has a solution, and then try to derive this condition that GCD is 1, right? So we first assume that the GCD of ABC is D for D strictly greater than 1, and then we try to arrive at a contradiction, right?
So I mean, why did you arrive to a contradiction?
Yes. So the thing is, if I assume that D is greater than 1, right, and we know that this has a solution, right? So since this has a solution, since D is the GCD, so D must divide A, D must divide B, and D must divide C, right? So then I can write like this, right? A, B, C, I can express like this, right? So when I put it back, so I have D times of this thing is equals to 1. So then D divides 1. So that is a contradiction, right? Because I have assumed that D is strictly greater than 1.
That's why D cannot be greater than 1. Could be
Right.
either
So D,
equal.
yes, D has to be exactly equal to 1.
Yes, okay, I understand that part. And then.
And conversely, we assume that the GCD is 1 and prove that this linear equation has a solution.
Okay, and then what we do there, okay, we assume that GCD is 1, and the GCD of A and B is G.
Right. So GCD is 1. So now we can assume that GCD of AB is some G. And by Euclidean algorithm, I know that there exists solution to this linear equation. Right? Capital X and capital Y you can find using Euclidean algorithm, right? But since the total GCD is 1, that is the total three quantities. So what we have is the GCD between G and C has to be 1, right? Otherwise,
1, yes.
this will be violated. So now again using Euclidean algorithm, I know that there exists W and Z such that this happens. So now I substitute the value of G here.
Yep.
And we get this.
And then you have.
So then we check that this. So this is a solution.
I mean, that must be a solution, and the GCD of that would be 1.
Right.
Okay, so that's like the condition. Okay.
Yes. So this is the So because of this condition, we get that this is a solution. XW, YW, and Z. So this is a solution.
Okay, so coming back to the point C.
Right.
We will start by saying that the GCD of that is equal to 1,
Right.
right?
So first you have to prove that the GCD of these three quantities is 1. So then we can move. So then we can move like the previous thing to find a solution.
Mm-hmm.
Right. So how can we do that?
Maybe we can start just by grouping. So let's
Yes.
say that the GCD of 155x and 341y is G, and then we just
Yes. Yes. So that we can start. So let us try to find it. So we can first find the GCD of 155 and 341. So yes, what will be that?
okay. Uh, we need to do Euclidean algorithm for that. I think 31.
31, right?
Yeah.
Okay. So I think what we are having is 134 equals to 2 times 155 plus 31, right?
Uh-huh.
So from here actually what you have is 31 is nothing but 34 minus or plus minus 2 times 155, right?
Yes.
Right. So this is
Yes.
our G according to part B, right?
Yeah.
So next step is to find and this is our X and Y, capital X and capital Y, right?
Yeah.
So okay, so let me
That
write
was
down more clearly. So this is actually 1 times this thing. So
yeah.
this is my capital X and this is my
I think the other way around. I think.
yes, yes. So this is Y and this is X, right?
Yeah. Yeah.
All right. So now we have to the next step is to find the GCD between G and C, right? So G is
Yeah.
31 and C is 358. So next step is
Mm-hmm.
the GCD between 31 and 385. Right. What will be that?
31.
Hmm.
Oh, sorry, 13. No. Yes, 13. No.
No.
I mean, must be 31, right? Because 31 is a prime number.
Yes, yes. 31 is a prime number. Yes. 31, I think, that does not divide 385, right?
Oh yeah, you're right. You're right. I mean, would be 1, right? Because that's what we are assuming.
Right. So the thing is, this has to be 1. So now apply Euclidean algorithm to find those variables.
Okay, 385 is equal to 12 multiply 31,
Right. Plus.
13.
Right. Next we have 31 equals to
2 multiply 13 plus 5.
right. So this is
2
also
multiply 5 plus 3. 5 is equal to 1 multiply 3 plus 2. 2, 3. 3 equal 1 multiply 2 plus 1.
Right. So we received, we got already. This one is our
Yeah.
GCD. So now I think we
Mm-hmm.
can backtrack. So, so from here, if we start, so 1 is nothing but 3 minus 2.
Mm-hmm.
So that is 3 minus 5 minus 3.
5 minus 3.
Right. So next step will be
Minus 5. Okay, 5. No. 3, right? We need to replace with
right.
3.
So
3 is
it's
equal to 13 minus 2 multiplied 5.
right.
Mm.
So
2 times 13
hmm.
minus 5 times 5.
Right. So next step will be
Then 5, we replace 5. 5 minus 5 multiplying 31 minus 2 multiplied 13.
okay.
That would be 12 multiplied 13 minus 5 by multiplied 31.
Okay.
And then 13. 385 minus 12 multiplied 31 minus 5 by multiplied 31. Huh? That would be 149.
Yes. 144 plus 5. 149 times 31. Right.
Yes, so we have that.
Okay. Just check. Let me check. So 12 times 385 minus 149 times 31. Yes, that is correct. So now, yes. So that is my. mm, so this is my W and Z, right?
Yeah.
So what I get is uh, so minus 149 times 31 plus 12 times 385 equals to 1.
Uh-huh.
So this is my W, this is my G, and this is my Z. So this is my C, right?
Mm-hmm.
Okay. So then what will be the solution? So solution is we have to substitute back this 31, right?
Mm-hmm.
So this 31 you have to substitute back here. So from here what I have is minus 149 times. So 31 what I got is 1 times 341
Uh-huh.
and minus 2 times 155. So
Mm-hmm.
plus 12 times 385, right?
Mm-hmm. Yeah.
Right. So this is equals to 1. So from here, okay, so ABC the ordering was I think uh, is 15 155 was the first term. Okay. So it will be 2 times 149 times 155, right?
Yes. Yes. Plus
Plus minus 149
minus 49
times,
multiplied 341 plus 2.
right. So 2 times 149 is I think how much?
Again, 298.
298, right? So the solution will be so XYZ 298 minus 149 and 12.
Yes, and that is only because we assume the GCD is 1. Otherwise, we wouldn't be.
Yes, yes. So that
Uh,
is yes. So that is the condition to have a solution. But that is all. That is true, right? For this case, because if you check the GCD of these two quantities is 31, and we have checked the GCD between 31 and 385 is 1. So it forces that the three of them should have also GCD same, right?
yep.
Right. So means from this condition and this condition. So actually we'll have that GCD of these three terms. So this is actually 1, right?
Yes. One.
Fine.
Mm-hmm.
Okay, so let us try to do the next one.
So, okay, this is actually a linear equation, right?
Yes.
Um, so
So
this is
yes.
just like a strategy to find a solution because if we don't assume that the GCD is one, I mean there are more solutions in the scenario where the GCD is not one.
No, no, no. The thing is, if it is GCD is not one, then we are always not sure that whether solution exists or not. So the thing is, we can definitely say when GCD is one, we can definitely say that a solution exists. So that is the thing.
Hmm.
Okay.
Okay.
Okay. So the question 5, what they're saying is, so suppose GCD of AB is one, and prove that for every integer C, so prove that every integer C, the equation ax plus by equals to C has a solution. Has a solution in integers. Right. So how to get it? The question is clear, right?
It says to prove that the equation is that it's like a more general equation, not just equal to one,
Yes,
but
yes, it is
C.
equal to some C. So if we know that the GCD is AB is one, then we can tell that always it has a solution.
So you're saying if we assume that the GCD of A and B is equal to one, there's always a solution.
Right, right. Always this linear equation will always have a solution. So that is they are claiming here. Yes, we have to show that it is true.
Maybe we can start just by doing like a general. We can say that one divides.
One.
Uh, let's see. I mean, we can divide everything by C, right? And then we will have like A.
Uh, Divide by C, no, right? Because A and B is GCD is one, right? So they will not be integers, right? If I divide by C, so I want integer
I see.
solution.
Mm-mm.
So what you can do is, so we know that the equation. So the equation, if there was one, then it always have a solution, right? So if I change it, so suppose if I take this equation, ax plus by equals to 1. So this always have a solution, right?
Yeah.
So this is because the Euclidean algorithm and GCD is 1, right?
Mm-hmm.
So now we can just multiply the both side by c, right?
Okay.
So multiply both side by c. So then we have nothing but a times cx, right? Plus b times cy equals to c.
Mm-hmm.
So now, so this is our solution. So x we can take as c times capital X, and y you can take c times capital Y. So these are integers because capital X and capital Y are integers, right?
Mm-hmm.
So this is
I
fine, right?
see. Okay.
Right. So now using this property, they are asking to find a solution to 37x plus 47y equals to 103. Yes. So they are telling try to make x and y as small as possible. Yes.
But I mean, when you multiply both sides by c,
Both sides by?
I mean, by c, you're multiplying both sides by
Right.
c. I mean, how do you know where is the solution or how to get to a solution?
Yes. So what I'm saying is, so if I consider this equation, ax plus by equals to 1, right?
Mm-hmm.
So these always have a solution, right?
Yeah.
So that I know. So suppose the solution is capital X and capital Y.
Mm-hmm.
So capital X and capital Y be the solution. So then this is the satisfaction. Means this is how does it looks like, right? A times x plus b times y equals to 1.
Okay.
So if I multiply the whole equation by c, so then also it is true, right? So I am multiplying both sides by c. So it
Okay,
becomes
you're
cx,
multiplying both
cy,
sides by
and
c.
c, right?
Mm-hmm.
So for this equation, ax plus by equals to c. So my solution is cx and cy.
Okay, okay. You're just multiplying both sides, and
Right,
that
right,
that should remain equal.
right,
I mean, okay, okay, okay.
right, right. So now they are asking to solve to find a solution to this equation. So first you have to check the condition, right? So 37 and 47, what is the GCD?
37 and 47, the GCD will be 1, right? Because they
Right,
are prime numbers.
right, right. So the GCD of, right. So this is one. So according to that, our previous result, we know that this have a solution. We have to find it. So first use Euclidean algorithm.
Will be 37 something plus 47 something
Yes,
equal
yes.
to 1.
Right. So that is what you have to find using Euclidean algorithm. Right.
Okay. Let's see. 47 equal 1 by 37 plus 10.
Right.
37 equal to 3 times 10 plus 7. 10 equal to 1 times 7 plus 3. 7 equal to times 3 plus 1.
Right. So we got it. So one we got. So now trace back. So one equals
1 is
to,
equal to 7 minus 2 multiplied by 3. 7 equal to 2 times 10 minus 7. That would be 3 times 7 minus 2 times 10. And then 37 minus, yeah. 3 times.
Right. So next step will be
That would be minus 9. 3 times 37 minus 11 times 10. 3 times 37 minus 11 times 47 minus 37.
right.
That would be 15 times 37.
14, right? 11 plus 3.
14, yes, 14. 14 times 37 minus 11 times 47, yeah.
Right. So that is our equation. So what we got is
14, 37,
so that is 1,
1.
right? So right. So now what is our C? So C is 103, right?
Okay, yeah.
Okay. Okay.
So
So
you
if
can
I
just
multiply, right. So if I
everything.
multiply the whole thing by 103, so then what happens?
14 multiply 103. Okay, I mean, you will have the 37 and 47 still, but you would have a
Yes, only
different.
the coefficient we want.
So 14 times 103 is 1442.
Right. And I think this one is 1133. Right. 103. Right. So, but
Mm-hmm.
they are asking. So this is one solution. That is fine. But in the question they are asking, try to make x and y as small as possible. Right. So if you remember that we know the general solution we know, right? So so actually this linear equation have infinitely many solutions, right? So if you remember,
Okay.
we did one thing, right? So I think yes. So this so all solution we know, right? So of this form, right? Where k is
Oh yeah, I see. That was the solution.
right. I think we did here somewhere, right? So yes. So this was the solution, right? So if one solution I know, then I can write all the solution like this, right? So right,
Yeah.
right. So here GCD is 1, so this will not matter. So what will be the set of all solutions to this, right? uh, so all
X
solutions will look like,
X1 which be 40, 14, 42. Yeah,
right? So x1 y1 is 1442,
plus K times B,
right?
which is
So
11
uh, okay,
minus 11K.
1 minute. So this is which one is our, so 47 is our b, right? So if 47 is our b, so then it is minus b, right? So minus 47k, right?
Okay,
And it
so
is 1133 plus 37k, right?
mm-hmm.
So this is our all solution. So what can we choose k such that it becomes small?
I see.
So k is integer. So this is all solutions, right? Right. So I want to make this one as small as possible and this one also as small as possible. So what should I choose our k as?
I see. I mean, we can just, do like guessing.
Yes. So okay. So what is the nearest term? So 47 times how much will be near to 1442? So you can just divide, right? So you can divide and check what will be the nearest multiple.
Sorry, what do you mean?
No, the thing is, if I want to make the difference small, so then we'll take the nearest multiple of 47, that is nearest to this one, but less than that, right?
Uh-huh.
Yeah, so that's why we can just divide it, right, and check. So 1442 divided by 47, how much is that?
Very.
Right, so it is 30 point something 68, right?
Mm-hmm.
And 1133 divided by 37,
Very.
so that is also 30.62 something, right?
Yeah.
So if I take k equals to 30, then what happens? So if k equals to 30, then
32.
right, and the second quantity is
23.
minus 23, right?
And 73.
Right. So this is a solution. So this we can take, or if we want further the further small, then we can go to the next value also, right? So if I take k equals to 31, we can take either of them. So then you can check that this is nothing but minus 15 and 14. So they are asking to find as small as possible. So we can take this one as our solution, minus 15 and 14.
I see.
Okay. So you have to check which one works. So it can be either 30 or 31.
So if we
So
replace that, let's say 37,
yes, you can check. Minus 15 times 37 plus 14 times 43.
103.
Okay,
Mm-hmm. Yeah.
right. So that is our 5. So let us see the next one. 6. So 6 one is they are saying that sometimes we are only interested in solutions to ax plus by equals to c using non-negative values for x and y.
Mm-hmm.
Non-negative values of x and y. So the thing is, the solution here, I want it is both x and y to be greater than equals to 0, right? Sometimes. So for example, here it is not true, right? One of them is negative and one of them is positive, right?
Mm-hmm.
Right. So the part A they are saying is, so explain why the equation 3x plus 5y equals to 4 has no solution, where both of them are non-negative. With x and y, both of them are non-negative.
Yeah, I mean, we can arrive to the general equation, to the general form of the all the solutions, and maybe we will get a contradiction in the general form.
Okay, how?
Uh, we need to get to the general form, like all the solutions.
No, no, general form, I don't think we need that. So yes, you have to find some argument why no solution exists, where both of them I want to be greater than equals to 0. So the thing is there are pointing towards this. One of them has to be negative. So that is the idea. But why it is true?
Why? Sorry, what?
Yes, the thing they are asking, right? So no solution exists where both of them are greater than equals to 0, right?
Right.
So that is what we want to show. So how to show it?
Mhm. I mean, we need to get to a general form, right? Otherwise, how we're going to know?
Yes, we can show by contradiction also, right? Some contradiction we can get, right?
Hmm. So that the general form will cannot give us that clue that there's no
Yes,
solution.
general form we can means we can use the general form. That is fine, but that will be long, right? Or that is so. What I want to say is general form is to be a heavy tool to use to find this condition. So this condition is very simple, so that we can without using general form also we can do it. Okay, let us see it. So suppose we assume that there is a solution, right? That x is greater than 0. So suppose
So the GCD is not one always over here, right?
GCD, no, GCD we don't know about anything. So for this equation, I know that GCD is 1, but that is not in general.
Okay, okay.
Okay. So suppose if I take that x is positive, greater than equals to 0, and y is greater than equals to 1, right?
Mm-hmm.
So then 3x plus 5y is greater than equals to 5, right? Because y is greater than equals to 1,
Mm-hmm.
right? So equal to 4 is not possible because I want it equal to 4. So this case is not possible, right? So y
Sorry,
has
sorry,
to be 0.
sorry. What do you mean? Equal, greater and equal than 5? Why?
Yes, because this is positive, right? So x is positive, so it is greater than equals to 3 times 0, right? And y is greater than equals to 1, so it is plus 5 times 1. So it has to be greater than equals to 5, right?
Yeah, because it's at least 5.
Right, but I know that this is 4 that is given to us. So this is a contradiction, so this is not possible, right?
Okay, so it's not possible that x would be greater than 0 and y greater than 1.
Right, so that is not possible. So this forces that y has to be 0, right? Because y greater than equals to 1 is not possible, so y has to be 0, right?
Mm-hmm.
So if y is 0, then 3x plus, so if y is 0, then 3x plus 5y is nothing but 3x, right?
Mm-hmm. Yes.
Right, but then also it cannot be equal to 4 in any integer value, right? Because if I
Yeah.
put
There's no.
0, 1, 2, anything if I put, it cannot reach 4, right?
Right, right, right.
So there is no solution. So hence, there is no solution. If we assume uh, that both of them is greater than equals to 0. Okay.
Hence, there is no solution. So just by testing these two scenarios, x greater than 0 and y greater than 1, or y equals 0, I
Right.
mean, we can say that the conclusion will be that there is no solution.
Right. Okay.
Mm-hmm.
Right. So next part, what they're asking is, so part B they're asking is, so make a list of some numbers of the form 3x plus 5y, where both of them are positive. X is greater than 0 and y is also greater than 0. And then make a conjecture to values which are not possible. Okay, first let us check for what values it can have.
But I think we just proved that there is no solution when.
No, there is no solution to equal to 4. So it can have other things, right? So they are not restricting anything. So they are asking, if I take x greater than 0, y greater than 0, what are the possible values this can take? So there, that we can put the values and check, right? So that is simple.
Mm-hmm.
Okay. So tell me.
I mean, we can start by x zero equal 0.
Yes. So if you take 0, 0, so then yes, then we get 0. Then if we take 1, 0, then we get 3, right?
3.
Then what else?
Then if we take 0, 1, that would be 5. If we take 1, 1,
Right. So
we
0, 0
get
gives 0, 1, 0 gives 3, and 0, 1 gives 5, right? So then
1, 1,
8 we
8.
get 1, right? Right. 9 we can also get, right?
9 would
Can we get
be,
9?
yeah,
So it's
3,
3 times
3
3,
plus 0.
right? 5 times 0. 10. What about 10?
3 times 0 plus 5 times 2.
Right. 11.
11 would be 2 times 3 plus 1 times 5.
Right. 12 we can get easily. What about 13?
1 times 3, 2 times 5.
Right. 14 we can get as 3 times 3 plus 5 times 1. And 15 also we can get easily. 3 times 5 plus 5 times 0, right?
Mm-hmm.
So then what you can see is, so from 8 to 15, every number I can write, right, in this as a linear combination of 3x plus 5y, right?
Mm-hmm. Yeah.
So each number, so between 8 and let us see 15, right? So this I can write. So 3x plus 5y equals to c has a solution where x and y both are greater than equals to 0, right?
And that is only because we didn't go beyond 15.
Right. So between 8 and 15 we have all thing, right?
Yeah.
So what can we say? What can you say if c is greater than equals to 16? Can you say something from here, from this observation?
I mean, we don't know.
Yes, directly we don't know, but can you say something? That is the thing.
Can we, what do you mean, like just a guess?
Not exactly guess, but from some observation can you do?
I mean, we can assume, right, that it's possible to find not natural numbers like that. I mean, 16 wouldn't be possible, right?
No, 16
Actually,
is
it is
possible, right?
possible.
Yes,
Yeah, it
16
is
is possible
possible.
because we have already expressed. So we have already expressed 8, right? So if I multiply it by 2 on both sides, I know that 16 also have a solution, right?
I see. What about 17? There's no.
No, 17 also it's possible, right? Think about it. So 17 we can, yes, that is the idea. So they're asking to give a conjecture, right? So the conjecture is any number that is beyond 8, we can actually express it.
Um, yeah, I mean, we can say that it's possible to get all numbers
Okay,
from 8 onward.
right. So how to show that?
How to prove that?
Yes, how to prove that any number or beyond 8 we can write as 3x plus 5y, where both x and y are non-negative.
How to prove it? Um,
So what you can do is, so 16 is there, right? So
we
suppose,
can we can
yes,
do like I mean, we know the GCD of 3 and 5 is 1,
okay.
and then we can find like the x and the y, and then we multiply that by c.
Uh, no, that is not always not possible because so by Euclidean algorithm, so that gives us integer solutions, right? But that does not make sure that both of them are non-negative, right? Because if you see the integer, if you see always the Euclidean algorithm, right? So
Yeah,
this
includes
gives
a negative
one
one.
negative and one positive, right?
Yeah.
So that does not give that all of them are greater than equals to 0. So Euclidean algorithm actually we cannot use here. So that is the idea.
Okay. Okay. Mhm.
So what we can do here is actually, so any number which is greater than equals to 16, we can write it as some 8 times some d, we can divide by it, or plus e is the remainder where e lies between 8 and 16. So this we can do, right? Any number,
Mhm.
right?
Okay.
So any number we can do like this where e lies between
Yeah.
8 and 16, right?
Yeah. Mhm.
Okay. So then what we can do? So we know that since e lies between 8 and 16, I know that e can be expressed like this, right?
E can be expressed like that. Yeah.
Right. So since e lies between 8 and 16, so e can be, I have an expression that e equals to some 3u plus 5v, right? So I can express like that where u and v are both positive, right?
So E is just a reminder, and you can.
Not exactly remainder, but because we are remainder is when I divide by 8, the remainder is between 1 and 8, right? But it here it is I am deliberately doing it between 8 and 16.
Okay.
So okay, so if I explain it a bit more, so the thing is, so when I divide by 8, then my quotient is q and remainder is r, right? So here the remainder lies between 0 and strictly less than 8, right?
Yes.
So what I'll do is I take uh, a factor out. I make it q minus 1 and then take 8 outside, right?
Uh huh.
So now if I take this quantity r plus 8, so now this is my d and this is my e. in this equation.
Uh-huh.
So now I can say that E lies between 8 and 16, right? Because I
Yes,
have
you
added
added
8 on
8.
both sides.
Mm-hmm.
But also I know that D is also is positive because it is greater than 16, right? So it since C is greater than 16, Q is at least 2, right? It will start from 2 because it is 2 times 8 plus something.
Uh-huh.
So if I do -1, still it is positive, right? So that is
Yeah.
what we are using here,
Okay.
right?
Yeah.
Right. Now since E lies between 8 and 16, I know that E have a expression like this where both U and V are greater than equals to 0.
Wait, where the 3u plus 5v comes from? I know, yeah, that's because of the equation, right?
No, no. This so this we explicitly saw for all values between 8 and 16, right? So for all values of 8 and 16, we explicitly found the expression, right?
So you're saying, but that is only between 8 and 16.
Right, right. 8 and 16. So that is what I'm saying, right? So between 8 and 16.
Yeah, but u comma v then will also have another constraint. It cannot be just greater than 0. It needs to be like between 1 and 5.
1 and
Yeah,
yes, that is
because
fine.
if,
That is
uh-huh.
fine. But means at least they are positive, right? Greater than equal non-negative, right? That we want only.
Yeah, they are positive, right?
Non-negative. So that only we want. So that is fine. Now what will we do is, right. So now we'll follow from here. So the what we have is C equals to 8D plus E, right?
Mm-hmm.
So 8D plus 3U plus 5V,
Okay.
right?
Yeah.
Now this 8D I can replace by 3D plus 5D, right?
Okay, okay.
Right, now I take the 3 common. So it's D plus U plus 5 times D plus V,
Okay, okay.
right? So I know that D is greater than equals to 0 and UV are also greater than equals to 0. So that makes these two quantities also greater than 0 and greater than 0, right?
Uh-huh.
So any
Yeah.
number where C is greater than equals to 16, I can express it as some 3x plus 5y, where x equals to D plus U, y equals to D plus V, and both of them are positive, not negative.
Mm-hmm.
So that is the conjecture, and we have proved the conjecture, right? So any number that is bigger than 8, means from 8 and onwards, I can actually give an expression like this.
Mm-hmm.
So that is the same. Make a list of numbers of the form 3x plus 5y where both are non-negative. So any number which is greater than equals to 8, we can.
Make a list of some numbers on the form, and then make a conjecture. So that conjecture is
Yes, the conjecture is, let me write down. So any number, suppose C, greater than equals to 8, can be expressed as 3x plus 5y equals to C, with x comma y both are non-negative. So this is what we proved, right?
I see.
Fine.
Yep.
So we showed that from 8 to 15 all of them are possible. Then after 15 we show that we will use those expressions only to find new solutions to when the number is bigger than 16.
Mm-hmm. Yep. Makes sense.
Fine.
Yes.